Welcome to The Explainer. Today, we're cracking open one of chemistry's best-kept secrets, the oxidation number. Think of it as a secret accounting system that lets us track the movement of the most important particle in chemistry, the electron. So let's kick things off with a huge question that chemists wrestled with for centuries. In any given reaction, you've got literally trillions of electrons zipping around, making and breaking bonds. How in the world do you keep track of that invisible chaos? Well, the path to an answer was a pretty long and winding one. For a while, the best idea was this mythical substance called phlogiston that was supposedly released when things burned. Then, the brilliant chemist Antoine Lavoisier figured out it was actually about oxygen being gained, which is where we get the word oxidation. But the real game changer was finding the electron itself. And then finally, W.M. Latimer came up with the formal system we use today to actually track them. And that brings us to this incredibly clever solution. Chemists essentially invented an elegant and, okay, maybe a little bit deceptive, bookkeeping tool. Let's pull back the curtain on what the oxidation number actually is. Okay, so here's the big idea. An oxidation number isn't a real charge. It's a hypothetical one. It's the charge an atom would have if we just pretended that every single bond it made was totally ionic, meaning electrons were completely given away or stolen. It's a powerful what-if that helps us balance the books. And that difference is absolutely crucial. Think about something like table salt, NaCl. An electron really does jump from sodium to chlorine, creating real measurable charges. That's a real ionic charge. But the magic of oxidation numbers is that we can apply the same logic to everything else, even a molecule like water, where electrons are just being shared, to get a feel for who's pulling on those electrons a little harder. And that's really all it is at the end of the day, a brilliant accounting system. It's not a perfect picture of physical reality, but it is an absolutely essential tool for figuring out where the electrons are moving and shaking during a reaction. Now, you know any good accounting system has to have a clear set of rules, right? So let's open up the instruction manual and see how we actually assign these numbers. These 6 rules are pretty much everything you need. Rule 1, any element just hanging out by itself, like a piece of iron, is 0. Easy. Rule 2, if you have a simple ion, its number is just its charge. Then you have our superstars. Oxygen, almost always a -2, and hydrogen, almost always a +1. And the most important rules, 5 and 6, tell us that the books have to balance. All the numbers have to add up to 0 for a neutral molecule, or to the overall charge if it's an ion. Okay, that's enough theory. The best way to really get a feel for this is to put the rules to the test. So let's solve a little chemical puzzle together. Here's our challenge, nitric acid, or HNO3. Now, our rulebook gives us a number for hydrogen and for oxygen, but what about the nitrogen in the middle? Well, that's what we have to figure out, using the other atoms as our clues. All right, step 1, let's fill in what we know for sure. Our trusty rules tell us hydrogen is a +1 and oxygen is a solid -2. But wait, we have 3 of them, so that's a total contribution of -6 from the oxygen side. That just leaves our nitrogen as the big question mark in the middle. And now we bring in rule number 5, which is the key to the whole thing. Since nitric acid doesn't have an overall charge, it's neutral, all these numbers have to add up to 0. So that +1 from hydrogen, plus whatever our nitrogen is, plus the -6 from all the oxygens, has to equal 0. So we just have a little bit of simple algebra. +1 plus our unknown minus 6 equals 0. To make all that balance out, our nitrogen has to be +5. And just like that, puzzle solved. Okay, but let's ask the most important question. Who cares? So what if nitrogen is +5? What does that number actually let us do? Well, this is where the bookkeeping suddenly becomes incredibly powerful. This is how we understand everything from batteries to rust. Because these numbers finally give us a rock-solid definition for 2 of the most important processes in chemistry. We can now say, definitively, that oxidation is when an atom's oxidation number goes up. It's lost a little control of its electrons. And reduction is when its number goes down. It's gained a little more control. And check this out. This is the payoff right here. Look at this reaction. By calculating the numbers, we can see exactly what went down. Copper started at 0 and ended at +2. Its number went up, so it was oxidized. Silver started at +1 and ended at 0. Its number went down, so it was reduced. It's perfect. We can literally see the electron exchange just by tracking these numbers. Of course, this is chemistry we're talking about, so there's always a twist. The oxidation number is a fantastic model, but like any model, it starts to get a little weird at the edges, and that's where things get really interesting. So let's look at a funky little ion called thiosulfate. If we just run the numbers using our rules, oxygen is -2, times 3 is -6, the whole ion is -2. A little math tells us the two sulfur atoms must have a total of +4 between them. So, on average, each sulfur atom has an oxidation state of +2. But here's the catch. That's just an average. The reality is actually much cooler. In the real molecule, the two sulfur atoms are in totally different positions. One is right in the center, and the other is stuck to the outside. Because they're in different spots, they have very different jobs. And more advanced models show that their individual oxidation numbers are more like +5 for one and -1 for the other. Our simple rules just gave us the average of those two numbers. And this really gets at a crucial piece of wisdom from chemists Janssen and Wettig. They said that we need to define concepts like this as precisely as we can, but we have to always remember what they are when we use them. In other words, the oxidation number is an amazing model, a super useful tool, but we can't ever forget that it is just a model. It's not reality itself, which leaves us with a final, and I think really fascinating question. What does it actually mean when our simple accounting trick gives us an average, or when different scientific models give us different right answers? It means we found the edge of our simple tool, and by doing that, we get a peek into the much deeper, much more complex, and frankly beautiful world of chemical bonding that lies just beyond. Thanks for joining me on The Explainer.